Radio, sorry about that. It only goes for 15 minutes and I fell for it again and I was blabbering away and I kept doing a whole nother question until I realized that it actually stopped recording. So sorry. Okay, so we've been given an angle in the center of this diagram. Notice that, okay, it's a right angle, but we have been given it. So if ever we're given an angle at the center, it's kind of like if we see parallel lines, it's a bit of a clue that we'll probably need parallel line rules. If there's an angle at the center, then maybe, just maybe, we'll need that angle at the center being twice the angle at the circumference rule. Okay, and we can use that in this one here. So as I've shown you in my little purple diagram there, of course, normally it looks like that, but remember that day I showed you that little graphic thing that you could spin it around, you could drag that angle around the edge, you could drag it all the way around. So instead of always looking like sort of an arrowhead like that, you could have your angle in the center, but you could actually have your angle at the circumference way out there, you know. So it can actually look quite different. And you'll see that in this case, we have that going on here. So our angle at the center is our right angle there. But check it out. We've got this guy here. Okay, angle BAD. That's actually half of our 90-degree angle here. So angle BAD is 45 degrees, okay, because of that rule. What angle is it that we're trying to find at the end of the day? X. Yeah, so therefore now that we know that BAD is 45, then we can, of course, happily find angle X by doing 122 minus 45, okay, to get whatever that makes, and I can't quite remember. So that, I think, was a merit question, wasn't it, that one? All right, now this guy here, I've just started the working on it, just because I had to wait for the last video to load up, so I thought I'd make good use of my time. So this one here, I've written it all out nice and neatly as well to show you guys an example of what we need to be seeing to be getting the maximum amount of marks that we can get. So question D here, it's just a diagram, there's no cats involved, there's no scratching posts or anything. And so we're just asked to find an angle. So here we are, we've got some angles here that we know. Many of you fantastically could see the feet and the hands, you know, pointing up. So straight away you got onto it and you worked out that this guy here, DAE, was 25 degrees. Okay, that's the first step I've done in my working there. You'll see I've written the reason beside it, angles on the same arc. Then what a lot of you also did then was you worked out that this guy here is 98 degrees. Okay, and in the working there, I've shown you how we would lay that out, just reminding you with those nice reasons beside it. Okay, so we've got those two angles there. We go, all right, well, what could we find next? Well, we could figure out from angles in a triangle, from this triangle here, we can now work out what that third angle here is, can't we? So let's do that. Take away 98 and 25 from 180, leaves you with 57. And we've got our feet and our hands again, so this guy over here needs to be 57 as well. Okay, so as well as putting them on my diagram, notice I've written them nice and neatly, step by step, over to the right-hand side there. All right, so that was ADE that we've just worked out, wasn't it, or ADB, either way. All right, so the next thing we've done is gone, okay, remember that we were told that this here is an isosceles triangle. These guys are the same, those two sides there. So since we've just worked out that angle ADB is 57, then that means angle ABD must also be 57 degrees. Okay, so that's this next step here. All right, next thing. So we've got all of that so far. We're like, all right, remember at the end of the day, we want to figure out ADC. So we've got to work out BDC down here, don't we? So how are we going to get that? Well, what other rules have we got? Remember, we've got a circle going on here. We've got triangles. We've got no parallel line rules. They're not going to come into it. We haven't got the center, so we can't use our, you know, angle at the circumference and angle at the center rule. But we have got a quadrilateral, okay, don't we? And it is inside our circle, so it is a cyclic quadrilateral. And we know that with cyclic quadrilaterals, those opposite angles add to 180. Okay, so that's our last step, 180. We know 180 minus this big guy here will make all of this guy here. So we do that, 180 minus angle ABC gives us 82. So we know that all of this has to be 82 degrees. Oh no, sorry, it doesn't. I lie. Oh, bugger. I know that all of that 57 and 25 makes 82 degrees. How can I get rid of that? Oh, there we go, 8 and the 2. So all of this makes 82 degrees. So take that off 180 and you're left with 98. Okay, that's excellence. So getting 2 of these, okay, let's say that you did these first 2 steps. That was enough for merit. I believe it's so long as you had your reasons beside it. Hang on, we'll just double check that. I'm pretty sure that was right, but now I'm starting to doubt myself again. So yeah, if you got any 2 of them correct with their reasons, that was enough for a merit mark. How cool is that? If you got any 2 right, or 1 angle with a good reason, that was worth an achieve mark. So yeah, if you completed that whole lovely chain of reasoning, step by step, it's worth excellence. Okay, so I've got it there, and that'll be in the OneNote that you guys can look at just as an example of how you'd lay out that wording. Okay, what have we got? 2A. Now I have to keep an eye on the time and not go past 15 minutes again. So we're told it's got a parallel top and bottom, nice and easy. Most of you, oh my gosh, I think maybe everyone got this right. So again, a variation, so many different ways it could be done. Alternate angles. Some of you used co-interior angles, I think, at one point. But yeah, it was really beautifully done. I actually don't even want to go over that one. Question B, yeah, so this was your 3D Pythagoras. So you've got this weird looking diagram here, and it may help to redraw it kind of like a box. And we did this one during lockdown, all this 3-dimensional Pythagoras stuff. I have got videos on this YouTube thingy of mine, so if you want to go back and look at some of those worked examples of 3D Pythagoras questions, there are some on videos in here. So this is like the top of the box here, isn't it, with the 46 and the 35? That's that white part of the mat there. We've got our 15 centimeters going down, and of course the thing that we want to find, so let's just, the thing we want to find is going from the bottom here, which is where the ball is, from the bottom here up to that corner there, isn't it? So you might literally want to draw it in 3D, so you could do those inside kind of layers to help you. Sorry, that's not the best drawing there, but yeah, that might help you and give you a bit of a clue where to start. But it's basically going to be 2 triangles, okay, to get you where you need to be at, okay? We talked about this online, and we talked about it in class, and I talked about sort of imagining a hinge. Sometimes that can help, like on a gate, where you have, it can't move from one side. Here, you've basically got, this is your triangle here, isn't it? Okay, this is your right angle triangle that you're dealing with. So we can't work out this guy here. So you can imagine that like a hinge. It could go sort of, swing out this way, or it could sort of swing back that way. We need to find out a little bit more about this. So one length that we do know is this guy here, don't we? It's 15 centimeters tall. So we've got that part of it. But we don't know this length here, do we? And that is the other short side of this right angle triangle. So we actually need to find that first. And of course, how can we find him? Well, he is the hypotenuse of this triangle. Hey, yeah? So let's find that hypotenuse first. So we can repeat, remember it's the same lengths going along here, and that length there is 35 centimeters because it's the same at the bottom and the top all the way around. It's a nice cuboid. So yeah, off you go. So we've got x squared being 46 squared plus 35 squared, and that makes whatever it jolly makes. I'll use my calculator. I was just going to cheat and look at the answers. Hang on, I'll just pull. All right, so that makes 3,341. So x is the square root of that, which is 57.801. Okay, centimetres. So 3 different decimal points there. Okay, so lovely. We've now worked out that that x, that length along the bottom of our triangle that we are interested in, is 57.801 centimetres. 57.801. And then we've got 15 there. So we want to find this guy here. We can call him y since we've already used x for this particular problem. Let's now use y. Or you could use c if you like, because Pythagoras, we often use c. So y squared is also a hypotenuse, isn't it, of this triangle? So we're 15 squared plus 57.801 squared, which is whatever it's going to be. I need to clear all of this. 15 squared plus 57.0. 3,565. Sorry, I hate using my phone, but I don't have a calculator here at home. 9556. So I'm just having to do this on my calculator. That's why I keep pausing it, because on my phone calculator it's really slow. 0.9556. 59.7156. So we should round that to something sensible. 59.72 centimetres to 2dp. So we want to answer our actual thing. The distance from the back small ball to the opposite front corner is 57.72 centimetres. So that was question 2b, and that one was worth a merit mark. Okay, 59.7. Rightio. So what are we up to now? 59.7. Sorry, I made that a 57, didn't I? Cool. All right. So question C. Here's our little puss. Oh yeah. So each surface of the cat bed. So we've got the regular pentagon. They've told us it's regular, so that's great. We know all the sides are the same length. And we've been told this width of the cardboard around the edge there being 5 centimetres. We want to know the area of the inside of the triangle. Yeah, this was quite an interesting one, and I can't quite remember. Somebody had a cool way of doing it. I wish I had your test here. Yeah, I'm just going to have a look and remind myself how I did this. All right, so yeah, lots of you were really good at finding angles inside your pentagon here. I would do it the same way as what they've done in the answers here. There's not much else you can do, okay? You need to use some trigonometry. So it's a regular pentagon, so you can split this up into a bunch of triangles, okay? We know that those triangles are going to be isosceles. They've got the same lengths there. We also know that we could create a line right down the middle there and create a little right angle triangle. So if I were to draw one of those over here, let's say it's that one on the side there, okay? I've got this bit in here, which is 5 centimetres. I've got 28 centimetres altogether, so half of that's going to be 14. So for my right angle triangle, and let's now get rid of, that's going to rub out the whole thing, isn't it? Let's get rid of those edges and just now deal with the right angle triangle. That's going to be something that we can deal with, because we can deal with right angle triangles. So the issue is, of course, though, at the moment, we've only got that funny 5 centimetre length there. We've got the length of this side here, but we don't have any other measurement to go from. And this 5 centimetres isn't really any help right now. It's not going to help us find anything out. However, as many of you realised, we can